everyone, and welcome to AISC's webinar, Design of Underhung Hoist and Crane Girders, presented by Lucas Pockel. Today is May 18th, 2017. My name is Christina Harbour, and I am with AISC's Continuing Education Group. I'll be moderating today's presentation. I want to introduce today's speaker. Lucas Pockel graduated with his Bachelor's of Science in Civil Engineering from Michigan Tech University and completed his Master of Science at Lawrence Tech University. He's worked in the industrial and energy industries for 11 years and has spent time both in the office and on construction sites developing new and retrofit designs. He is also working with AISCE on a revision to their fossil fuel retrofit design guide, along with AISCE's publication on structural design of air and gas ducts for power stations and industrial boiler applications. Welcome, Luke, and I'll let you take it from here.
Thanks, Christina, and thanks everybody for joining. As Christina mentioned, we do have all these slides available for you, and there is a lot of content that we're going to be running through today. So there is a portion of this that I'm going to be moving through rather quickly, but I wanted to include all the backup calculations and information for you to reference after today's presentation. So before we get into the nuts and bolts of what we're going to be talking about today, let's quickly go through what is an underhung bridge crane system. So this is a very general schematic of an underhung bridge crane system, and the way these systems operate is you have an operator that is typically standing at grade or at an operating mezzanine, and they hold a pendant to control the crane system. This can either be a wired pendant, or at times we have wireless remote control pendants that operators will utilize. That pendant will operate a hoist and trolley assembly, which is up within the roof framing system typically of a structure. This hoist and trolley travels back and forth along a crane bridge or bridge girder and hoists the load that is being moved throughout a structure. The crane bridge or the bridge girder is typically supplied by the crane manufacturer and has end trucks, which are these wheeled assemblies on either end of the bridge girder. Those end trucks travel on the primary items that we're going to be talking about today, which will be your runway beams or girders. Common uses of underhung crane systems would be in heavy industrial facilities, other types of manufacturing or mill buildings, petrochemical facilities, as well as O&M facilities. The design and operation of these underhung bridge crane systems is similar to monorails. However, monorails do only operate in one direction. They do not include the bridge girder or end truck assemblies. The design is also similar to a top-running bridge crane system, but we're going to be talking about some very significant differences between the two types of designs throughout this presentation. Here we have another schematic of an underhung bridge crane system. This is within a pre-engineered metal building type structure where the runway members would be supported from the roof system. And I just wanted to include this to point out one particular item. Beyond what we discussed previously, the engineer typically needs to consider this runway electrification system. These are generally powered end trucks that do have motor-operated wheels, and so generally you need to provide enough clearance around any of your runway members to not only have the end trucks run on the bottom flange of the members, but also have this electrification system run on the top of the runway members. Here's another general schematic. This shows the end trucks a little bit better. And also includes a electrification system for the hoist and trolley itself. This would be your hoist and trolley assembly. And then there is an electrical festoon system that travels partially with the hoist and trolley system. Again, we need to consider this when we're doing our initial layout of the structural steel and the overall building structure around these underhung crane systems. This festoon system can be rather large and will need to be provided by the crane manufacturer, the design information and clearance requirements. Here's a picture of a typical underhung bridge crane system. Everything yellow in this picture is provided by Yale. a very common hoist manufacturer. Here you have your hoist and trolley assembly. Your pendant control would be this cable coming down to grade. And then you can see in the foreground here the end truck assembly on one of our runway girders. You have your bridge beam, your bridge girder here spanning between the two runway members. And then looking from the other direction, you can see the end truck, and you can also see the festoon system. That's what these looped cables are. That's the electrification for the hoist and trolley assembly. Typical underhung bridge crane systems can range up to about a 10-ton capacity for a single girder bridge crane. That would include one bridge girder assembly from the crane supplier. These typically can span all the way up to about 175 feet, and generally once you get into those very long span hoist assemblies, you will run into what's considered a multi-runway crane, which has over 2 runways. You need to be very cautious about differential deflection when you do get into those multi-runway cranes. That'll be outside of the scope that we talk about today. Larger capacity underhung bridge cranes can range typically up to about 15 tons with a double girder assembly. This will have 2 bridge girders spanning between your end truck assemblies, and the hoist and trolley system will travel between those 2 bridge girders. These can span up to approximately 200 feet, and again, with those long spans, you would run into a multi-runway situation. It is possible to get a capacity for an underhung crane system up to about 25 tons. However, the practical limit is between 10 and 15 tons because of the local flange bending effects of the bridge girder as well as the runway girders that we'll be talking about later. Typical capacities for these types of systems range anywhere from 1 to about 7.5 tons. So an overview of what we'll be discussing today. We've gone through a little bit of an introduction on what the bridge crane systems are, but we'll talk a little bit further about bridge crane information, general information, and types of runways that you can possibly be designing. We'll get into a little bit of the design guidelines and reference standards that are used and compiled for the design of these runway girders. Talk about some special design considerations and typical construction details. Then I've got a comparison of 2 example problems looking at a wide flange and a wide flange with a cap channel runway member. We'll briefly touch on some related topics as well as enclosed track and patented track systems just to let you know what all is out in the industry. And then we'll wrap things up at the end with some conclusions and lessons learned. What we have here is a plan view of a joist and joist girder structure. This plan in the upper left shows your joists spanning top to bottom on the page, and your joist girders are spanning left to right across the page. On the bottom right would be your crane runway system. The crane is identified here as a 3-ton system. And then we have these longitudinal members, which would be your runway members. And these smaller assemblies would be some infill steel, which you can see in this next slide. That infill steel, we have an elevation view of it shown here. This would be your bridge crane system hanging down below all of our superstructure above. Your runway members would be directly above your bridge. And then everything above that is used to distribute the forces to the roof truss system or roof joist system in this case. On the right, you see the steel fabricator's Tekla model and then the final installed assembly in the field. Typical crane information that's provided from a supplier. This is from one specific supplier. There are a number of suppliers out there, but I wanted to just include this for your reference. There's a very large amount of information that can be provided by a crane manufacturer if you are able to get them on board early on in a project. Some critical information that you can find on these drawings would be the maximum wheel load. This is the maximum load that you're going to need to design for at every wheel of the end truck. This is a section view showing that end truck with the crane girder below it. And this shows the wheelbase, WB, would be the spacing of your end truck wheels. That also comes into consideration when looking at these moving loads across your runway system. There's also an elevation view shown here of the entire bridge and end truck system. One critical piece of information that is not specifically tied to the design of the runway members, but is tied to the overall design of these systems, is this dimension from the bottom of the bridge to the high hook point. Many owners believe or specify a minimum clear height to the bottom of a bridge crane system, and you need to ensure that that does account for this difference in elevation between the bottom of the bridge crane and the high hook height. This is as high as this crane system can pick, and you need to make sure that whatever the owner is going to be hoisting within their facility, this elevation can accommodate that pick. Another very important piece of information is this bridge weight shown in the table. We'll discuss this a little bit further as we get into the design load generation, but if you can get the bridge weight from the crane manufacturer, that's going to make your job as a design engineer much easier. There's also a number of different types of runway members that you can design. Typical runway design would utilize a wide flange shape. A couple shortcomings on these wide flanges is they tend to have, as their name would imply, a wide flange, but it is also a relatively thin flange. That causes local flange bending concerns in the bottom loaded flange of the runway member. If you have a longer span member or a highly loaded member, you may want to utilize a cap channel on top of a wide flange. This typically will not be used to resist lateral forces of these underhung crane systems, but rather will be used to brace the compression flange and increase the lateral torsional buckling stability of your runway system. Standard or S shapes are also a very good system. These do provide a narrower and thicker bottom flange, which helps with the resistance to local bending effects. However, you want to make sure, due to the sloped top flange surface, you want to make sure that this is specified to your crane supplier early on in the project so that the proper wheels or end trucks can be specified and provided for your system. And similar to the wide flange sections, to increase the lateral torsional buckling capacity and assist in bracing your compression flange, you can add a cap channel as well. The patented track and enclosed track systems noted here we'll discuss a little bit later, but they are also items which can be specified and typically would be purchased by a project. There are a number of different design guidelines and standards that are utilized. There's no specific code that specifies the design of these underhung crane systems. IBC and AISC E7 do provide impact factors for crane loads, but they're very vague, and AISC E7 actually does not even include load combinations for crane loading. The AISC 360 specification, that obviously will be utilized to develop your allowable strength criteria for your runway members, and also the fatigue considerations that we'll discuss shortly. ASME provides a publication, NUM1, which can be very useful in reducing the impact factors that AISC E7 specifies. This is only possible, though, if you know the operating speed of the hoist, trolley, and end truck. That will all tie into the impact factors. AISC provides two very good design guides, which also can help in the design of these underhung crane runway systems. Design Guide 7 for industrial buildings includes actually a complete design example for a top-running crane system, which would be very similar to this underhung system. And then Design Guide 9 provides torsional analysis recommendations and guidance, which we'll also be highlighting briefly in this discussion. AIST put out a Technical Report 13, the design of mill buildings. This provides a lot of load combination criteria that is generally used for the design of these crane systems. And CMAA, the Crane Manufacturers Association of America, Standard 74 as a specification for these underhung, underrunning trolley hoist systems. There are the crane ratings and also the installation tolerances will all come from that CMAA 74 document. As always, AISC does provide free downloads. The specification, the structural steel specification, AISC 360, is available for free download, and the design guides are available free to members and for a small charge to the general public as well. This is CMAA 74, the specification for underrunning hoist and trolley systems. And this is where you're going to start developing your design criteria for these underhung crane systems. As you begin your design, you need to consider a vast array of questions which are not typical for a general superstructure design that we would be used to. It's generally good to discuss with your owner how they're going to be utilizing these crane systems. How many cranes will they have within a particular runway or within a particular bay in a building? How many of these cranes can be expected to operate or are possible to operate simultaneously? Sometimes owners have multiple cranes within one runway, and one is identified as a maintenance-only crane. However, if that crane is able to be operated during the same use period as the primary crane, you may want to consider both cranes operating simultaneously. You should discuss with your owner how often will these cranes lift their maximum load. What allowance should be made for impact? Do they have operators that are very hard on their equipment, or are they relatively smooth operating personnel, and are the code-specified minimum impact factors acceptable? What lateral thrusting forces can you assume to occur simultaneously, especially if you have multiple cranes in the same bay? If you have a roof-supported system, how stiff is that roof, and what loads on that roof may be present during the operation of these crane systems? And then also we discussed the clearances around and below the crane system. What else is going to be present within the structure? A lot of that information is going to tie directly into developing the CMAA service classification of the crane. There are 4 service classes, A through D. It's a very infrequent service to very heavy service class. And these classes are based on 2 specific criteria. The specific loading or range of loading that's expected to be hoisted by these systems, as well as the number of load cycles that are anticipated for the life of the crane system itself. The load cases range from L1 to L4, again, very, very lightly used, up to regularly loading near the crane assembly's rated capacity. And then also how many load cycles are anticipated. This is the number of picks that are made per shift times the number of shifts per day times the number of days in the entire life cycle of the crane. So this is an estimate used generally at the beginning of the design phase based on the owner's experience in most cases. You'll then take those load class and load cycle criteria and enter CMAA 74 Table 2.6-1, and this will help you define the service class of your crane, A through D. Once you have your service class, we'll start developing the design loads that we need to consider. Now there's 3 primary impact loads that need to be considered. You have vertical impact. This is obviously a vertical load due to the inertial effect of either starting or stopping the picking motion on a load for the hoist and trolley assembly itself. There's lateral crane loads, sometimes called side thrust loads, which are oriented perpendicular to these runway members that we'll be designing. These lateral crane loads can be due to multiple effects. It can be the inertial effect of this hoist and trolley system traveling along the bridge crane itself, along the crane girder itself. It could be hitting this end stop on the crane. It could be a skewed load being picked by the operator. or it could be due to the runway members themselves being slightly skewed, or the end trucks on the bridge crane assembly itself being slightly skewed and causing an accidental lateral force on this runway member. That's where we'll discuss the CMAA installation tolerances. They're very critical to ensure we're not imposing unanticipated loads on our runway system. There are also longitudinal forces that need to be considered. These are due to the entire bridge crane assembly traveling along the length of the runway. It could be due to starting and stopping the bridge crane system itself and the end trucks, or it could be due to the end trucks hitting these end stops on the ends of our runway members that we'll be designing. So not only is the information from the crane manufacturer essential in determining these proper forces, but the installation, as I mentioned, of these runways can lead to a substantial amount of additional load consideration. This is not only at the initial installation, but also throughout the service life of a crane system. It should be noted to the owner, make sure they are aware that regular maintenance and inspection needs to be considered during the service life of these cranes to make sure late in life we're not accidentally imposing unanticipated loads on these systems. The loads that we need to specifically design the runway systems for include a maximum wheel load. This may be provided by the crane manufacturer, or if you need to calculate it, the way that you would calculate it would be take the bridge weight and evenly distribute that bridge weight to your end trucks and each of the wheels within the end truck. Then you would take the rated capacity of the hoist and trolley assembly, as well as the hoist and trolley assembly itself, locate that near one of your end trucks, and distribute that force to the total wheels on one end truck, and that will give you your maximum wheel load. Impact forces, like we discussed, include the vertical impact, which ranges anywhere from 0 to 25% of the maximum wheel load. This varies based on the usage of the crane. If you have a manual bridge crane system, which in this instance would be pretty rare, you actually have a 0% vertical impact factor due to the slow motion of the crane system. And it ranges anywhere up to 25% for a pendant operated or a cab operated structure. Lateral side thrust forces, according to AISC 7, these are set at 20% of the rated capacity plus the hoist and trolley weight. You'll note that this does not include the bridge weight. That is because the side thrust forces are generally due to the hoist and trolley assembly starting and stopping lateral motion along the bridge. The bridge is not moving in this direction, so we don't need to consider an inertial effect of the bridge itself. To account for potential differential lateral stiffness of your runway systems, it's generally recommended to apply 60% of this side thrust to one set of wheels, to one end truck. If you have a known differential stiffness between your two runway members, for instance, if you're using a wide flange on one side and on the other side of the structure, you require a built-up section. It would make more sense to develop a 3D analysis model or a FEA model to determine what that distribution should be. This lateral side thrust load acts horizontally at the surface between the runway beam and at the top of the bottom flange of the runway beam, and acts perpendicular to the beam itself. The longitudinal tractive force, again, is due to the inertial effect of the entire bridge crane system moving along the length of the runway members. And this is specified as 10% of the maximum wheel load, according to AISC 7. Again, this is due to the maximum wheel load because the bridge beam itself is moving in this direction. Again, this force will act horizontally at the surface between the end truck and the top of the bottom flange of your runway member. One other item that needs to be considered is the end stop force. This is either the hoist and trolley assembly hitting an end stop on the end of the bridge girder, or the end trucks hitting an end stop on the end of your runway member itself. There's a couple of different end stops that can be specified. You could have a rigid end stop or a buffered end stop that does absorb some of the energy that is exerted by the impact of these moving systems. This should be specified on your structural construction documents to make sure that whatever is provided out in the field is in alignment with what was used in your design consideration. As I mentioned before, IBC does not provide much guidance, and AISC E7 does not provide any guidance with regard to how to combine these crane loads. So for load combinations, we typically will move into the AIST Tech Report 13 recommendations. This tech report does provide general minimum guidelines for both single and multiple cranes acting within a single bay, as well as what load combinations should be considered for your repeated loads or for your fatigue analysis, which we'll be discussing a little bit later. These are general guidelines on general rules of thumb, and your initial discussion with your owner should either confirm or modify these load combinations slightly. Here I've just defined all of the items that were utilized in load combinations previously to define all the different notation for you, so we won't run through all of those. Additional design criteria that needs to be considered and included in your construction documents includes confirmation that all runway beams need to be straight, parallel, and at a constant elevation. The construction tolerances here are specified by CMAA 74, Table 141-1, which I'll show you on the next slide here. These are more restrictive and stringent requirements than the AISC standard of practice. So your contractor needs to be made aware of this early on in the project. And there are also deflection limitations that need to be considered. L over 450, or the span of your runway member over 450, based on the maximum wheel load without impact, will be your vertical deflection criteria. And lateral deflection criteria is L over 400 due to the maximum side thrust. Angular twist should also be considered, and a lot of times crane manufacturers will provide recommendations or maximum rotational tolerances for their crane systems. This is that runway tolerance table that I alluded to. Here we've got the criteria for, or tolerances for, the bridge span itself, or the crane span. We have anywhere from 3/16 to 3/8 of an inch, depending on the overall span of the bridge itself. Straightness tolerances, so this would be the lateral alignment of your runway itself, 3/8 of an inch. Total deflection or out of tolerance is allowed, and a 1/4 inch rate of change in 20 feet is the allowable angular deflection or misalignment of the runway systems. In elevation, again, you have vertical tolerances provided here, and then also differential tolerances, specifically on the bottom picture here. Elevation tolerances between your two runway members, your bottom running crane runway members. There's a very tight tolerance here to make sure that that runway is sitting parallel to the floor. Another design consideration is unbraced flanges. Due to the clearances required around these crane systems, both compression and tension flange unbraced lengths can be a concern. With compression flanges, you can consider adding a cap channel, like I mentioned previously, for longer spans or heavy bridges. And for continuous runway members, you want to make sure and consider the lateral torsional buckling effects on the bottom flange at the runway supports. That will, your stresses will transfer into compression stresses at those supports, so lateral torsional buckling does need to be considered. It's important to note that a cap channel is not always the solution. You'll hear me reiterate that a couple of times through this. There is a trade-off to the strength that you gain with these cap channels, in that you're adding extra weight to the channel as well as labor to weld those two sections together. We also need to recognize that the design of these underrunning systems is different than the top running systems in that the addition of a cap channel is not directly going to resist the lateral forces or is not greatly going to improve your lateral stability of the system or lateral strength of the system. It actually is possible to hinder the overall strength of the system. We'll talk a little bit more about that shortly. And then continuity. We need to determine and consider, do we want a simple span runway system or a continuous span runway system? Simple span, it's generally not the most efficient design. It's generally the easiest design. However, it's also very easy to unintentionally introduce continuity through connection plates between adjacent runway members or runway ends. So you need to be very cautious about where you locate girder splices or how you detail the specific supports of the runway girders with a simple span. It's more common and generally more economical to design continuous span runway systems. This will minimize the number of crane girder splices, which can be quite expensive. You'll also generally have a higher C sub B value and lower deflections. But as I mentioned previously, you do need to consider lateral torsional buckling of these girder bottom flanges at supports. You can treat these support conditions similar to a cantilever, which we'll discuss later on. And in order to treat them as a cantilever, you need to locate that inflection point, which would then be treated as the end of your cantilevered member. Also, load height. General design criteria and design loading criteria assumes a load application at the neutral axis of a structural member. We all know this is pretty rare. And when you have a top flange loaded crane runway member or a top running bridge girder, this actually will decrease your lateral torsional buckling strength. If you can imagine, as your girder begins to buckle laterally, you get a small amount of deflection. The vertical load that's applied at this top flange as it deflects now has an eccentricity introduced into the system, which provides an additive rotational force, therefore reducing your buckling strength. With bottom flange loading, like what we're talking about today, you actually get an increased resistance to this lateral torsional buckling because that deflection of the compression flange as it begins to buckle leads again to an eccentricity, but our resultant moment is going to resist that tendency to buckle. Let me show you that here. The Structural Stability Research Council has come up with guidelines on how to incorporate this into your design. You can see at the top here, this is the general loading application assumption. As you have top-loaded members, this vertical force, as the top of your member begins to deflect, creates a rotational moment leading to an increased ease of buckling. However, when we have a bottom flange loaded member, as we get lateral deflection of the top flange, we actually are resisting that movement through our vertical force at the bottom flange. You can actually get up to a 40% increase in your C sub B value with the use of, or when you're designing for bottom flange loading conditions. And we will utilize that through our example. Cantilevers are also a special condition that are very common with these, really any type of crane system. You may see these where the tips of crane runway girders extend outside of a building so you can pick up deliveries off of the bed of a truck and hoist them into the building, or within a building where you're trying to cantilever your crane system over perhaps a mechanical piece of equipment or a specific area where our friends, the architects, are not allowing us to put any of our superstructure. In order to account for this cantilever situation, David Nethercott is a professor in London, and he developed two different methods. One uses effective length factors, K sub C, and the other uses a modified C sub B factor to account for this modification to our bending capacity of our members. When we're using the K sub C effective length factor, we need to make sure we are considering C sub B equal to 1 in our analysis, as all of these K sub C values were derived assuming C sub B is equal to 1. As I mentioned, there was also another procedure that was published in which the K sub C value is set equal to 1, and then there's a modified C sub B factor. But since we're relatively used to the effective length factor with column design, it seems a little more intuitive to use the K sub C factor. I've got a link here to a good modern steel construction article from 2005, which actually walks you through the full load and then development capacity using this K sub C factor. And here's a table showing the K sub C factor for different loading conditions. You will initially determine the cantilever support condition, whether you have a fixed cantilever or a propped cantilever, and then what your support flange bracing conditions are, whether both top and bottom flanges are braced or just the top flange only. And then you'll look at the tip condition of your cantilever itself, whether it's free, top flange braced, or top and bottom flange braced. And then the loading application location, if you're on the top flange or any other case. And then you've got your K sub C values that are tabularized for you. Let's look at a real quick example problem. If we have loading that is not at the top flange, the root of the cantilever or the nearest support is only braced at the top flange, and the tip is completely unbraced. If we go back to that previous slide, you've got the top flange of your cantilever is braced, the tip of your cantilever is completely unbraced, and you have non-top flange loading, you will wind up with a K sub C factor of 3. This is then used to modify your allowable moment capacity. You can use this, as I alluded to earlier. You can modify this method to look at continuous beams and also laterally unsupported beams with varying end restraints. So it's a very useful design procedure. Torsion is an inherent problem with these underhung crane systems as well, due to the location of the force application. Just kind of as a reminder, any lateral forces applied outside the plane of the shear center of a member will result in a torsional force on your structure, your member, or your system. The shear center, or the center of twist, is that point within a specific member with which you must apply a force to avoid any rotation. So you can see at the bottom of the screen here, with a doubly symmetric section that does coincide with the neutral axis of your wide flange section in this case. However, with a channel or with a combined wide flange and cap channel, that shear center does not coincide with the centroid of your singly symmetric members. So that can lead to additional torsional effects that need to be considered as well. When considering torsion, there's two principal components that you need to look at: the pure torsion, or St. Venant torsion, and then warping torsion stresses. The most critical stresses that we need to consider for these wide flange sections would be the flange normal stresses resulting from warping of the cross section. Usually the pure torsional shear stresses are not a major factor with the magnitude of loads that we're talking about. You need to make sure you combine these forces based on Chapter H of the AISC specification for combined loading. These are additive, especially when you're looking at the normal stresses in the warping torsion. Those are additive to the flexural stresses that are developed within your runway members. AISC Design Guide 9 provides a very thorough torsional analysis procedure for steel structures. Design Guide 9 identifies the AISC manual, which provides some very good, very comprehensive torsional properties. You also may need to calculate torsional properties for built-up shapes. You need to make sure if we are inducing tension into any areas of your structural system due to this torsion, that fatigue stresses are considered. You should also make sure and review the angular twist of the section due to this side thrust load, either through computer analysis or Design Guide 9 does provide a procedure for this angular twist determination. Instead of this very detailed and thorough torsional analysis, there is kind of a quick and dirty approach which uses an analogy between torsion and flexure of a portion of your member, which is relatively easy to include in your analysis, relatively intuitive, and it is generally pretty conservative, generally on the order of 10 to 30%. So here's that analogy. You have torsion on your runway member. This is approximately equal to the moment couple forces acting on your top and bottom flanges. You then would take this horizontal force and apply it to the top flange or top flange and portion of the web and analyze that portion of the beam as a simply supported beam in flexure. The beam section itself used here would either be, for simplicity, you could look only at the flange dimensions to look at the flexural strength of the flange itself, or you could include perhaps up to maybe a third of the web in the resistance to that lateral force. And then fatigue. This is the big consideration that most people don't consider since it's so different from typical structural analysis. The AISC specification includes in Appendix 3 the design requirements for fatigue. Fatigue design applies to members subject to high cycle loading within an elastic range of stresses of frequency and magnitude sufficient to initiate cracking and progressive failure. Now there's two specific items there that we need to look at. The elastic range of stresses, so the magnitude of that stress range, as well as the frequency of that stress range, and we'll define that shortly here. This applies to certain components within crane buildings, not just your runway members or monorails, but also bracing, tiebacks, hangers, connections, etc. This is not only a consideration for the runway members themselves. And a note, the stress range, it's not the maximum tensile or maximum compressive stress that any point in a system is subjected to. It's the numerical sum, the difference between the maximum tensile and maximum compressive stress. The range is the full stress cycle that a specific point on a system will experience. And you would always evaluate these fatigue stresses at a service level. Now, frequency, we said, is one of the critical items that we need to look at. Fatigue does not need to be considered for a system that is subject to less than 20,000 cycles in its lifespan. Also, the magnitude was the second item that we needed to consider. AISC specifies a threshold stress range, F sub TH, which is the maximum stress range for an indefinite design life. So if your design stress range is above this threshold stress range, then you need to consider fatigue in your analysis. If a component or an area of a component is completely in compression, you do not need to consider fatigue in that instance. And also transient wind and seismic loads are not needed to be considered for fatigue design. Different types of bridge crane systems, as we discussed earlier, are determined based on their different service life. We talked about the 4 service classifications already, and I just wanted to note to everyone that if a client specifies a service class E or F underhung crane system, they're mistaken. The class E and F service classifications are actually for top running crane girder systems. And obviously the service classification was related to the number of load cycles and the load classes that we discussed earlier, so it ties directly into this fatigue analysis. Within Appendix 3 of the AISC specification, Table A 3.1 breaks different components of a system into 8 different sections, depending on exactly where you're looking at in the system. The designer would determine the design cyclic stress range, which we defined earlier. And then AISC specifies for these different areas within a system what the threshold fatigue stress range F sub TH is. If your design cyclic stress range is above that threshold, then you need to make sure that your cyclic stress range is below the allowable fatigue stress range F sub SR. This is at table A 3.1 in Appendix 3 of AISC 360, and you can see there's a relatively long definition of specific locations, the description of the location, and a visual representation of what we're looking at. In this case, we're looking at the interface between the web and the bottom flange of a typical wide flange member. And then you're given the threshold stress range, 24 KSI in this case, and then the C sub F constant. C sub F, you go back into the appendix, and this would then be your allowable stress range. So if your design cyclic set stress range is higher than your threshold, then you need to make sure that your design cyclic stress range is less than your allowable stress range, F sub SR. There are a number of different conditions, and actually I included this just to point out that it actually depends not only on where you are in the system, but the construction methods used within a system. In this case, you actually have a lower threshold stress range and a lower C sub F constant if you do not remove the backer rod from a complete joint penetration weld. That's the only difference between these two line items. Some recommendations for fatigue design. Talk to your client. We've discussed this before, but make sure you understand the expected use and the service life of the crane system. Understand the total number of load cycles, get an accurate number of load cycles that will be used, and state the CMAA service class on your drawings. It would be recommended to calculate the allowable stress range for a given stress category and design for that, but you can simplify your design by limiting the design stress range to the threshold stress range. However, this won't result in the most efficient design, and a lot of times you'll actually have clients that want you to design to only that threshold stress range. Some items to specifically avoid would be notching or putting any holes in the tension flange. Don't weld anything to the tension flange, especially cover plates or transverse welds across the tension flange. And try to avoid welded or bolted attachments. It's always good practice to try to clamp these systems whenever possible to minimize stress risers. Local girder effects is also a consideration. You need to look at these under the wheel loads. You need to look at both tension in the web as well as bending in the bottom flange. For web tension, a relatively standard approach would be to utilize or consider 3.5 times the K dimension of your runway girder as effective in resisting the tensile load. And then that would generate a tensile stress here of P over 7 times your K distance times the thickness of your web. And you would compare that to the allowable tensile stress of your web. Now remember, when we're looking at local effects, we're actually designing this member specifically, your runway member. However, you may have local effects on the members that are supporting the runway itself as well. So we need to be looking at the entire system as a whole, not just the individual components of the system. Local flange bending is also a consideration. This is flexure of the flange itself. We can generate the section modulus of a portion, an effective portion of this flange, as well as the moment that is induced by the point loads caused by the wheels, and then develop a design flexural stress in the flange. There is a similar but more extensive procedure for calculating these local effects in CMAA 74, which you can certainly use, and this procedure is always going to be a consideration for these underhung crane systems. And Christina, looks like we got a quiz.
All right, thank you, Luke. And we're going to take a break to just test your understanding of what Luke's discussed so far. This is an interactive question, so you can answer it by clicking on your screen and hitting submit. The question is, for underhung cranes, how are longitudinal crane loads applied to the runway beam? You can choose all that apply, so there may be more than one correct answer. At the top of the bottom flange, at the bottom of the bottom flange, perpendicular to the crane runway, parallel to the crane runway, as a percentage of the rated capacity plus the hoist plus the trolley weight, or as a percentage of the maximum wheel load. And again, you can choose all the answers that apply. And we'll give everyone a few more seconds to enter in their answers. Okay, let's see how we did. It looks like the most popular answers are at the top of the bottom flange, parallel to the crane runway, and a percentage of the maximum wheel load, and those are the correct answers.
Well done. All right, so let's take a look at a couple of typical crane girder details. On the right-hand side of this slide, you want to make sure and include longitudinal braces to transfer the longitudinal forces from your crane system into the superstructure. Now, if you have a joist system, which is what's shown here, you don't want to load the bottom chord of that joist. You want to make sure that your lateral forces are always transferred into your diaphragm above the runway system. And then the splice details that I mentioned earlier, these can wind up being very expensive. This is due to the need for a complete joint penetration weld at this bottom flange, grinding that smooth, removing this backer rod, and also the testing that's required for those complete joint penetration welds. So you can see how that would be quite expensive, and you want to try to minimize those if at all possible. Again, as mentioned, the splices are typically used with continuous spans. You want to minimize them. You want to put splices only where it's absolutely necessary due to available material lengths or installation limitations. You want to put these splices near vertical supports for ease and safety in construction, but not directly at the support, because that's where you're going to see your maximum negative moment occur. And as I mentioned, you need to have a smooth running surface at the top of that bottom flange. So you typically will provide a complete joint penetration weld and grind that weld smooth. Just a couple more quick details. Here's a typical runway hanger on the top left here. We've got hanger rods supported through a joist bottom chord. We've also got lateral support provided. You can see how if you have a force applied at this bottom flange, you're definitely going to be introducing a substantial amount of torsion on that system. And then on the right-hand side of the slide here, we've got a crane hanger with a lateral brace, again, similar to the longitudinal brace that we saw on the previous slide. Here's that elevation view that we saw earlier. This is showing supplemental steel that is needed to help distribute that vertical runway force, the load that's induced by the crane system, to multiple roof joists. This is typically good practice to try to reduce the stresses in these joist systems. And then just a couple of more lateral brace details, lateral support details for your runway systems. Here we've got a sloped roof system, so we have to have supplemental steel, again, distributing the forces to panel points within these joists. And then we have long span joist or truss systems. These can be a substantial challenge due to the installation tolerances of the steel as well as of the runway itself. Some lessons learned from long span steel joist construction. You have a vertical deflection criteria due to the crane wheel loads of L/450. In order to accommodate that, you probably are going to need to limit your roof snow load deflection to L/360. which is substantially tighter tolerance than what IBC recommends. You also want to look at your crane runway supports so that the differential deflection between successive points under the crane wheel loads is limited to 1/4 inch in 20 feet. This actually is derived from those CMAA installation tolerances. If you have crane runways parallel to the joists, you'll want to probably include some distribution steel like we saw on the previous slide to engage multiple joists in the support of these runway systems. You want to locate the crane runways symmetric to the supporting joists to avoid differential deflection and rotation of these runway members. Provide lateral and longitudinal bracing for the runways and the support systems to make sure you transfer these loads to the top chord of the joists and the roof deck, as we saw in the previous details. And wherever possible, provide for vertical, lateral, and longitudinal adjustment in the detailing of the support systems for rail alignment. This a lot of times can be accounted for or accomplished with the use of clamping systems. Also try to detail the support so that you have height adjustment to accommodate dead load deflection in your superstructure. You could either utilize shims or through bolts with adjustable nuts to provide some vertical adjustability. And also, if you're designing these runway systems within a joist and joist girder type structure, there are no SJI design standards for fatigue loading. So early on in the project, try to engage the joist manufacturer and joist designer and provide the AISC recommendations for fatigue criteria so that we don't run into a fatigue concern later on in the project. You may not have it with your runway, but remember, we need to be looking at these designs as a complete system, and the joists and joist girders are a part of that system. Make sure your installation contractor knows that they need to meet the CMAA tolerances in all directions. Make sure that that CMAA figure is included on your design documents and construction documents. And it's always good to work with your selected crane manufacturer and the joist supplier to make sure everyone is on the same page with regard to your design criteria and the developed details. Now I'm going to run through an example problem. This is going to be pretty quick. I'm not intending to run through every number, but this is just to show a comparison of wide flanges versus a wide flange plus cap channel assembly. So I've included all of the numbers for you, so you can refer back to this after the presentation. So this is just a plan view of our design. We have a superstructure that has bays at 25 foot on center. We have a 7.5 ton underhung bridge crane system. We've got our 2 end trucks that have wheel spacing at 6'3". And then this is our hoist and trolley assembly, which has a 1 kip dead load. The balance of our design criteria, it's a single electric pendant operated hoist. This will tie into our vertical impact factors. The bridge weight was defined by the manufacturer as 6.35 kips. The trolley assembly, as I mentioned, is 1 kip provided by the manufacturer, and then the maximum vertical wheel load is 10.1 kips. This is given by the supplier in this case. And then you can develop your maximum side thrust and longitudinal forces based on the AISC E7 criteria noted earlier. And then, as I mentioned, we're going to design a simply supported, just for ease of the example, wide flange and a wide flange plus cap channel. We'll use ASTM A992 steel for these sections. So initially what we will do is determine the maximum moment with regard to P, the maximum wheel load, and also the deflection. We can get these from the AISC manual design tables within Section 3. We'll then determine what the maximum allowable vertical and horizontal deflection is based on the L/450 and L/400 criteria. Calculate our design strong axis and weak axis moments based on the forces that we came up with previously, as well as an assumed 75 pounds per foot runway girder weight. And from this moment and allowable deflection, we will choose a W16 by 57. The properties that we'll need are all shown here. The unbraced length being 25 feet, that is greater than our L sub R value, so we need to make sure and consider lateral torsional buckling in this design, so we'll have to develop that F critical. F critical, based on section F22 of the specification, is shown here, and that equals 27.8 KSI in this case. We used a C sub B of 1.2 for this F critical development, and C is equal to 1 for doubly symmetric members. Now, since the load is applied at the bottom of our tension flange, we can multiply C sub B by 1.4 per that Structural Stability Council recommendation from the previous slide. So we actually have a modified F critical of 38.9 KSI. We multiply that by our strong axis section modulus, come up with our nominal moment capacity, divided by our omega factor, and we come up with our allowable moment capacity of 179 kip feet, which is greater than our moment demand of 127 kip feet. We'll then look at the weak axis bending, come up with our nominal weak axis moment of 79 kip feet, our allowable weak axis moment of 47 kip feet, and then we'll check biaxial bending of the top and bottom flanges, not including torsion in these instances, using equation H1.1-1b, since we do not have any axial load that we're accounting for. We're not including the end stop forces in this example. And our combined strength ratio is 0.87. So we meet the criteria for strength. Now let's look at local effects. The design moment, the demand stress, F sub B, is 0.75 times your wheel load over the thickness of the flange squared, or 29.6 KSI. And then your allowable flexural stress, 0.9 times 50 KSI, would be 45 KSI. So we meet the criteria for local effects as well. Now you can see based on this criteria that based on the local effects, as well as the deflection criteria, we could have reduced the beam size. However, biaxial bending governed in this design. Now let's look at a wide flange plus cap channel. We're going to look at a W16 plus 36 with a C12 by 20.7. These, luckily, the AISC manual, table 1-19, provides the section properties for this combined section. And looking at specification section F4, we need to determine if lateral torsional buckling applies. So we need to determine L sub P as well as L sub R. So I'm not going to go through these long calculations, but you develop an R sub T factor, moment of inertia factor of a portion of your runway member. This includes the C12 plus the top flange or the compression flange of your member and 1/3 of the compression region of the web. And you get an R sub T value of 3.85 inches. From that R sub T, you can develop an L sub P value of 102 inches and an L sub R of 452 inches. So our unbraced length of 25 feet or 300 inches is between these two values. So we'll then develop our nominal moment capacity based on AISC specification equation F4-2. Come up with an allowable moment capacity or a nominal moment capacity of 358 kip feet. We used C sub B again of 1.2 for this analysis, and we can again increase that C sub B by 1.4 based on the bottom flange loading. So we have a modified nominal moment capacity of 502 kip feet, and this is less than the R sub PC MYC criteria of 346. I'm sorry, that's actually greater than the 346 kip feet. So this will actually be governing in our design. So the lateral torsional buckling does not govern what you would expect when you add a cap channel. So our nominal capacity is 346 kip feet, and the allowable moment capacity then would be your nominal capacity divided by your strength reduction factor. And we have an allowable moment capacity of 207 kip feet, which is higher than the wide flange alone. Again, we'll go through the minor axis bending checks. You'll again get a higher weak axis bending capacity. And if we look at our combined strength ratio, we're at 0.7, where we were at 0.87 with the wide flange alone. So we definitely have additional reserve capacity with this cap channel. If we look at local flange bending then, this is where we have the problem. Due to the reduced thickness of our bottom flange, we now no longer meet the local flange bending criteria and would need to actually increase our wide flange to a W16 by 50 in order to make this combined section work, which would lead to a substantially heavier section than our wide flange alone. Obviously, we would need to do additional checks, including all of these listed here, the items that we discussed previously. But you can get the idea that there are definitely some advantages to just trying to use wide flange sections. It's possible, and generally you can provide a lighter section depending on your runway span and the loads that are applied. And you don't have any additional shop fabrication involved with regard to welding multiple shapes together. There are advantages to having a wide flange plus a cap channel. You have a higher weak axis moment strength to reduce those side thrust loads, and you have better torsional properties. A general rule of thumb would be if your wide flange plus your cap channel is 20 pounds per foot lighter than the wide flange alone, that's probably a more economical design. A couple of related issues. Curved members. Typically you don't see curved members in these bridge crane designs, but with monorails you do. Wide flanges and S-shapes are used at times, but they don't make great curved member runway members or monorails due to their low torsional section properties. Box sections or enclosed sections that we'll be discussing shortly make a much better curved runway member. And torsional stability of the curved members are achieved through the interaction of these girders with the diaphragm above. You must consider some additional torsion due to this curved geometry, additional side thrust, and resulting torsion due to centrifugal forces of the hoisted load moving around the curve. And in this case, your pure torsion will need to be considered. That will become a higher consideration. AASHTO provides some good recommendations if you need to design these curved runway members, and it's also recommended to support these members much closer, usually 5 feet or less if at all possible, and you'll need to complete a computer analysis to analyze these completely. Clamping systems I mentioned. We can use an engineered or fabricated clamping system or a pre-engineered clamp. There's 3 main things that you need to consider here. Initially, the structural design performance. With an engineered design or a fabricated design, you'll need to run through a bolt design, the clamp member design, as well as the support design. The figure on the right here is a typical Lindapter clamp, which is a pre-engineered example. Quality control is also a consideration here. With fabricated clamps, there's no standardized testing. If you're independently designing these clamping systems, no one is confirming that everything is done to your design standards or your design considerations. Workmanship of the fabricator and proper installation are absolutely critical in these installations, and it varies quite a bit from installation to installation. If you have a pre-engineered clamp, manufacturers do perform internal QC. They do random product testing with regard to dimensional tolerances, impact tests, and whatnot. So you get a higher level of confidence in what you're getting out in the field. And then you look at the economic cost of the connection. This considers design, material, fabrication, and installation. And it has been seen that up to 17% savings can be achieved with the use of pre-engineered clamps versus fabricated clamps. Here's a list of some advantages of the pre-engineered clamps versus the fabricated clamps. I'll leave that to you to read after the fact. And here's a couple of pictures of clamping systems that have been installed throughout different industries. Some offshore rigs, some very heavy-duty loads can be achieved through some of these clamping systems. Now we talked about wide flange, combined wide flange cap channel, and standard section runway members. There are also enclosed track and patented track systems. These are systems that are typically driven by client requirements. You will generally not be designing these. You will be specifying them, and usually process equipment will drive the need for either of these enclosed or patented track systems. For enclosed track systems, there are ANSI standards that are similar to the CMAA requirements, similar duty classifications as what CMAA has. Specific installation and fabrication tolerances are specified for these as well. And here's what a number of them look like. You see the enclosed system, and then you would have a trolley system that would run on the inside surface here of the tube shape, the enclosed shape. And here's a number of the manufacturers that do provide those that you can specify. For patented track systems, again, we've got ANSI design and fabrication standards, installation standards as well. Here you can see they are able to take into account a number of the considerations that we have to look at with standard runway member design. Here you can see a very thick compression flange or runway flange, and then here you see a very strong compression flange to resist lateral torsional buckling. Here's some of the typical suppliers for these patented track systems. And in summary, the design of underhung crane systems is often overlooked by the design team. It's a single component design. You need a large amount of detailed information from your client or owner, and usually the structural engineers are too busy designing the primary superstructure and foundation to consider what really can be viewed as a very small portion of the design procedure and process. But these runway systems have performed very successfully when you understand the parameters of the crane, how it's going to be used, what the life cycle is of the crane system. If you limit the applied stress ranges to acceptable levels for fatigue, you avoid stress concentrations at very critical locations by maintaining a continuous and uninterrupted tension flange. If you perform initial survey of the runway to make sure the installation tolerances are all met, and then also perform periodic maintenance and make sure you educate your owner that they need to be performing periodic maintenance. So the top 10 takeaways. We need to recognize that the design of these underhung crane systems is not the same as a top-running crane system. We have very little documentation that tells us exactly what we need to do, but a whole bunch of little pieces and parts that we can put together. You need to understand the intended crane use, lifespan, load cycles for the system with which you are designing. Make sure you coordinate with the bridge crane manufacturer, if at all possible, to verify the stack-up dimensions for clearances, available hook heights, type of end stop, etc. If you can't communicate or coordinate with them early on in the project, make sure you communicate your design basis as well as those CMAA runway installation tolerances on your construction documents. Allow for all of the impact forces as well as the load combinations per AIST Tech Report 13 or your interview with your client early on in the project. Recognize that strength and deflection limitations are not the only thing that need to be checked and may very well not be the governing factor in your design. You need to look at torsion, fatigue, local effects, stress risers, specific details within your design are very critical with these runway systems. Remember that built-up shapes may not be the most efficient solution for compression flange bracing. It may be much more efficient to just upsize your member. Allow for adjustability in the runway to the primary superstructure connections to allow for construction tolerances of both the runway and the superstructure itself. Use prefabricated clamp connections with fully pre-tensioned bolts where possible. This helps with installation tolerances as well as limiting stress concentration. And due to the number of checks and the detail with which these designs need to be done, it would be recommended to develop a design checklist to make sure as you repeat these designs, you don't miss some of the critical impact or the critical factors that will impact your design. So here we've got a number of reference documents that were used to develop this presentation or that are used regularly in these underhung system designs. So please refer to those as well. They're very good references and learning materials. And AISC does have a number of technical resources does have a number of good technical resources available for everyone. The publications website, frequently asked questions, and the steel interchange all provide very good information that design engineers can utilize for these underhung crane systems. And Christina, I'll send it back to you for the follow-up quiz.
All right, thank you very much, Luke. Thank you for that presentation. We will get on to the question and answer portion of this webinar, but first, another question to test your understanding. The question is, adding a cap channel to an I-shaped underhung crane girder will improve which of the following characteristics of the beam? And you can choose all that apply again. Does it affect the flange local bending, the weak axis bending strength, the torsional resistance, or the economy of the beam? And again, you can choose all that apply. You're adding a cap channel to an I-shaped underhung crane one way. That will improve which of the following characteristics of the beam? Okay, Luke, let's skip to the results here. It looks like almost everyone selected weak axis bending strength and torsional resistance. And we had about 21% of people said economy of the beam. Can you comment on that one?
Yeah, the economy of the beam, that's kind of a trick question, Christina. The economy of the beam could be an answer. Again, depending on if you can reduce the overall weight of the runway by about 20 pounds per foot, then you would be increasing the economy of the beam of the entire system. So that is a could be answer. But okay, yes, otherwise the weak axis bending strength and the torsional resistance would be improved by the cap channel.
Okay, and can you explain why the flange local bending would not be improved?
Yeah, the cap channel would be applied to your compression flange or your top flange, and all of your wheel loading would be applied to the bottom flange or your tension flange. So you don't actually get any load distribution from the end truck wheels to that cap channel itself. So the local bending takes place on the bottom flange, and your cap channel would only be able to be applied or installed on that top flange.
Okay, thank you, Luke. And let's move on to question and answer. I'm going to take us to slide 31. We had a couple of questions on this slide, specifically the longitudinal tractive force of 10%. Can you reiterate, is that a percentage of the maximum wheel load of just one wheel, or is that of all the wheels?
So technically it would be of all the wheels. Generally what is done is you take each independent wheel load and you would apply a tractive force. There is friction between every wheel and the top running surface of that bottom flange. And so you would take a percentage of the maximum wheel load of one particular wheel and apply it at multiple locations. That would be similar to the lateral side thrust load. In the application of these forces, you would actually apply these forces at each wheel load. So you'd have to distribute the 10% for the longitudinal tractive force or the 20% for the lateral side thrust. You would distribute that resultant force to each set of wheels and apply to your bottom flange appropriately. That's why that wheelbase or the wheel spacing that we saw in an earlier slide, that's why that wheelbase is critical, because you do have to apply multiple wheel loads at one time, which can substantially impact your moment diagram on your both strong axis and weak axis design.
Okay, thank you very much. And then also on this slide, that 10% and then some of the other loads that you apply, for example, the lateral side thrust of 20%. Can you tell us what codes those are found in? Is it AISCE, AIST, AISC?
Yeah, these specific factors, the 20% and the 10% for the lateral and longitudinal forces respectively, those are directly pulled from AISC E7. There are other criteria that are included in AIST Tech Report 13, as well as the ASME NUM1 specification, which do provide different impact factors, but these are the specified impact factors based on AISC E7 or the IBC 2015 specifically for this case.
Okay, thank you very much. And then we have a question on deflection. What is your position on the fact that runway beam deflection is limited to L over 450, while buildings are limited to L over 250 or L over 300? How does the building deflection relate to the crane beam deflection?
You really need to consider the entire runway and building, the portions of the building that are supporting the runway as a combined system. We actually recently worked on a design where we had to consider differential settlement in the footings as well, because we had different soil conditions along the length of our beam or the length of our building. So you need to look at the entire system and the general deflection criteria, serviceability criteria for building design for the specific components that are supporting the crane system. This goes both for underhung and top running crane systems. They may need to be tightened down or reduced to the criteria set forth for the crane systems as well. Excessive deflection in crane systems has led to a substantial number of crane problems or crane failures. It's a very big serviceability issue for the cranes themselves. So you should consider the reduction in allowable deflection of the overall superstructure based on this crane system. So I would say anything supporting the crane should meet the deflection criteria set forth by CMAA. And once you get into the top running crane systems, it's even a tighter tolerance as you get into the very heavy duty crane systems. As you get into the service class D, E, and F, your deflection criteria actually get substantially tighter. You have much less allowable vertical deflection on your structure. Your lateral deflection stays at L over 400, but for vertical deflection, it can increase or decrease to L over 800 or even L over 1,000 for some of the very high service class cranes. So that's why this needs to be a consideration very early on in the project, because if you're designing this crane system late in the project and trying to integrate it into a structure or trying to retrofit a structure with one of these crane systems, the deflection criteria is what's probably going to be governing your design, because you do need to design anything that's supporting that crane system for the crane system allowable deflection criteria.
Okay, thank you, Luke. That's very important.
Yep.
Thank you for answering that so thoroughly. I'm going to take us to slide 35. We have a question about runway tolerances. Does CMAA have a guidance in regards to runway beam gaps at splices? For longer runs, are there any design considerations for thermal expansion of the runway beams?
So typically the crane manufacturer will specify a maximum gap in the runway surface. A lot of times it's a 1/16 of an inch. It's very, very tight tolerance. That's to avoid binding of the wheel within that gap. That's another reason why the continuous span crane girders are preferred, especially by the crane manufacturers. It's a better running surface. With regard to expansion in a building, that's an extremely good question. I have not actually seen any effective way to transfer or to maintain a clearance between discontinuous runway members at a building expansion joint. That's an extremely difficult thing to maintain. You can I have seen some details where you can provide, it's almost a pivot piece that does allow at a building expansion joint. You preset the detail basically based on these CMAA tolerances, and that will allow the building to expand one way or another and maintain the continuous runway itself. But it's a very, very challenging detail to properly detail because it can also lead to stress concentrations if it's improperly detailed. So if you can at all avoid crossing over a building expansion joint with these crane runways, I would advise to do that. But if absolutely necessary, there are ways to do it. I haven't seen a great one that doesn't impose some sort of a stress riser or stress concentration at those splices.
Okay, thank you, Luke. The next question we have is in regards to this slide here, this diagram. Where do you apply the wheel loads for this local stress check?
So actually, if you look at the equation, E, the eccentricity, gets canceled out. It doesn't actually matter where you apply that force. As you see, let me get my little pointer here. You see you have the eccentricity in the numerator and the denominator, so it actually doesn't matter. If you do for some reason have loading on one side of a flange, or you're using, you have some sort of a specialty apparatus, the crane supplier may provide a dimension from a specific point on their trolley to the centroid of the wheel loading area. Or if you just need a rule of thumb, what I've done in the past is I've taken 2/3 of the distance from the center line of the member to the toe of the flange and use that as my load application location. But in balanced loading like we have here, that eccentricity actually factors itself out quite nicely, so you can actually apply it anywhere you want on the member. The reason being, as this force moves closer to the heel or to the fillet of this member, the effective area reduces by the same amount. The effective bending area reduces by the same ratio. So it doesn't actually matter in these combined cases where you apply that force along the flange length or width.
So a follow-up question relating to this. So for pre-engineered clamps or prefabricated clamps, it appears that the load's applied very close to the tip of the flange. So then, according to your explanation, that would not make any difference in the local flange bending.
Right. With those clamping systems, you typically, like if you use a Lindafter clamp, for example, like I had in some of the photos, you can get the diagrams of those clamps to see exactly where your clamp is going to be loading your flange. But as long as it's concentric loading about the center line of your member, it really will not matter. The farther out you are on the flange, the longer the effective length is right in here that will become engaged in the resistance to that flexure. Your S value here will increase.
So one more question relating to this slide. So should the local bottom flange bending stress be added to the runway girder bending stress?
Generally speaking, it will result in biaxial bending of the bottom flange itself. So within Chapter H of the specification, there is a way to look at the stresses the way we used to with ASD design, and you should apply these flexural stresses concurrently with the overall flexural stress of the wide flange and look at the flange itself. Look at the local or the combined effects of the two loading applications and two flexural directions concurrently. So yes, it should be added, but it will not be to the overall flexural stress of the beam. You'd have to look at the flange itself.
Okay.
And I can follow up with that the AISC spec reference section. I forget it offhand right now within Chapter H, which section it is in particular.
Okay, great. Thank you. We had a question on patented track systems. Are runway beams designed by the manufacturer when you use a patented track?
Yes.
System?
Yeah. Typically, you would specify the criteria for the design, or it may be that the process equipment that's driving this design will actually specify what track system is needed. But typically, yes, these suppliers will actually design their track system. We, as the engineer of record, would just need to specify the design criteria that they would need to incorporate in their design.
Okay, thank you. And I think we have time for another question. We'll just slip in one more, a quick one. Could you describe how do you determine the end stop impact forces?
There are a number of different ways that you can determine them. You can reverse engineer them. You can come up with an end stop that works for your system or that you've used in the past, and reverse engineer that to determine what the capacity is and list that on your construction documents. You can look at the F equals MA, so you can look at the acceleration and the distance with which you need to stop the end truck to come up with the force. So that would be if you're looking at a buffer end stop, or the preferred method would be if the crane supplier can specify that. If you have that information early on in the design, the crane manufacturer may prefer a specific type of bumper system, and they'll know the rated speed for their end trucks. So they may specify an end stop force, and if you have a crane supplier early on, they should be able to provide you with that information. But if you're designing something without a crane manufacturer known, there are ways within the AIST tech report that you can calculate recommended end stop forces based on your crane capacity. Or you could look at, what's something that works for me and basically offload that onto the crane supplier as well. So there's a couple of different ways, and it depends on how you're going to get the information to complete your design.
Okay, thank you very much, Luke. Unfortunately, that's all the time we have for questions today. There were a few questions that did not get answered during the webinar, so we will respond to you by email. Have a good day.